All right, welcome back. So today we'll be still looking at chapter 16. The focus of today will be on standing waves. So I know some of you guys play musical instruments. So basically, that's related to the standing waves you generate in the instrument. So if you are playing string instruments like a guitar or the piano, then you create standing waves in the guitar strings or the piano strings there. Okay. So let's take a first look at just the standing waves within the streams, okay? And then if you're playing other instrument like flute, that's then the standing waves in air columns. We'll look at that just in a little bit later. But for a standing wave in the streams, so we did this in the lab a couple of weeks ago, where you have a string with two ends fixed, then you can generate different types of the waves, right? So we're varying the tension in the string and then creating different numbers of loops in the string. So a standing wave is fixed in location, but oscillate with time, okay? So in this case, a loop you are seeing, so this string will vibrate up and down. One loop you are seeing is 1/2 of the wavelength. So then you should have two loops to be a complete wavelength of the wave. So for a string being fixed at the both ends, if the string is vibrating at most, we call it as antinode. And then when the location that the string vibrates minimum or not vibrating at all, we call them as nodes. Okay, so N for nodes, A for antinodes. So you can create vibration like this, or you can create a wave like this. So the string vibrate like this. They have antinodes here, and antinodes there. Or you can have something like this. Okay, so yeah, basically you can create different numbers of loops in the string, and that correspond to the different number of the harmonics. Okay, so for one loop, it's called the first harmonic, two loops, second harmonic, three loops, third harmonics. Okay, and this is also related to the frequency. So the first harmonic, that means you have the lowest frequency or the fundamental frequency. The second harmonic, you have a wave that has the second lowest frequency or second harmonic, okay, and then third, etc. Because in this case, you have just 1/2 of the wavelength, right? And that's the total length of the string. So then the lambda wavelength should be 2 times of L. In this case, you have two loops. Now the wavelength is L. So it's from 2L to L, right? And in this case, you have 3 loops. So then you have 2 complete loops as one wavelength. So this then wavelength here is 2/3 of the length. So your wavelengths are decreasing, your frequency are increasing in that sense. So for the first harmonic are called fundamental harmonics. So the wavelength will be equal to, or the frequency, wavelength is equal to 2 times of the total length of stream, but then the frequency will be equal to the velocity of the wave divided by the wavelength. So this is lambda. So basically, because frequency should be equal to wave speed divided by the wavelength. Okay. So then for nth harmonics, so n can be equal to 1, 2, 3. So 1 being the fundamental, 2 being the second harmonic, 3 being the third harmonic. Okay. So the frequency then is n times of the fundamental. Okay. So the wavelength then will be the fundamental frequency divided by n. Okay, so in that sense, because the first one will be equal to 2L divided by 1, the second one will be 2L divided by 2, so that would be L. The third one will be 2L divided by 3. Okay, in that sense. All right. So those are the equations to use for the different harmonics. And this is a visualized summary, figure summary here. So the first harmonic n equal to 1, second n equal to 2, 3, 4, 5, etc. Wavelength lambda sub n, the first harmonic wavelength is 2L divided by 1, second one will be 2L divided by 2, and third will be 2L divided by 3. The fourth one will be 2 divided by 4 because you are creating 4 loops here. So the total length L divided into 4, and 2 loops will be a 1 wavelength. So in that sense, okay. There's a link here. You guys can click on to and watch the trailer about the how some special people feels sound different than we do. They basically feel it's from the waves the sound generates. Okay, all right. Okay, so let's take a look on the example here. So it says a string 2.5 meters long with a mass of 3.6 grams is stretched between two fixed points with a tension of 91 newtons. Find the frequency of the fundamental. Okay, so in this case, you are given um, the length of the string, so L equal to 2.5 meters. Let me switch my camera. Okay, so L equal to 2.5 meters. And it says the mass attached on the mass of the stream is 3.6 grams, so kilogram. So this would be kilogram, okay? And 10 to the minus 3 kilogram. The tension in the string is 91 Newton. So it's asking you what's the frequency, the fundamental frequency on this string, okay? So for the fundamental frequency, I think it gives you this guy, the total length. So then if you go one slide back, you can find the fundamental wavelength is actually 2L. 2L divided by 1, right? So 2L. So you can calculate for your wavelength. And given the tension here, the total mass and then the length, that will give you the mass density, m divided by L, okay? So then you can use the equation of F divided by mu for the velocity. Once you have velocity, if you do velocity divided by the wavelength, that will be giving you the frequency. So F1 equal to V divided by lambda 1 in that sense, okay? So let's see what's the velocity first. It's 91 newtons over, down here you should have 3.6 10 to the minus 3 kilogram divided by, so divided by 2.5 meters, okay? And then you take square root. So that tells you this is 251 meters per second, the speed of wave in the stream. So then V divided by lambda would be like V divided by 2L. Okay, so 251 meters per second divided by 2 times 2.5 meters. Okay, so that will give you 50 hertz. About 50 hertz for your fundamental frequency. Okay. All right. So let's go back to the PowerPoint slide. Okay. Let's take a look on a second example here. So this one says you have two strings fixed at each end are identical, okay? Except that one is a little bit longer than the other one, so 0.560 centimeter, so a little bit over a half centimeter longer. Waves on these strings propagate with speed of 34.2 meters per second, so V is given, and the fundamental frequency of the shorter string is 212 hertz. What beat frequency is produced if each string is vibrating with its fundamental frequency? Okay, so to find a beat frequency, we then need to know the frequency, fundamental frequency of the other string. Okay, so let's take a look on the nonce given. Also, problem B, question B, it says, does the beat frequency in pi increase or decrease if longer string is increased in length? Okay, so we also look at that. But C says repeat pi A, assuming that the longer string is now 0.671 centimeter longer than the shorter one. So what will be the beat frequency? Okay. So let me see. Switch my camera. Okay. So on the second one, so let's sketch the problem. There's a shorter string, okay, and then there's a longer string, a little bit longer, slightly longer. Okay, so this is string number one, this is string number two. So the shorter string, it says that has the f1 of 212 hertz. Okay, so according to the equation, if we are looking for the fundamental frequency, that should be V divided by 2L. Okay, L1 on the shorter one. Now the V is the same on the two strings. Okay, so then we can actually find F, the fundamental frequency on the second one, because this is given, so this is also given, so we can find L1, right? So L1 can be found, then L1 plus that delta L should be L2, okay? So then we have that length. So then F2 can be calculated, right? So F2 then will be calculated by doing V divided by L2, okay? So looks like that's what we can do. So let's take a look on here. So this one will tell you that L1 equals V divided by 2F1. So 34.2 meters per second divided by 2 times 212 hertz. And that gives you 0.08066 meters, okay? Because the delta L is 0.560 centimeter, right? So that means it's 0.00560 meters, okay? So that's why I'm keeping this extra decimal places here, because this one has a lot of decimal places, okay? So to match up with this guy. All right, so then I can find my L2. My L2 would be L1 plus delta L. I'll just delta L, 0.08066 meters plus 0.00560 meters, okay? So that will give me 0.8 or 0.08626 meters, okay? Now I have that one, I can plug it into here to find my F2, okay? Or maybe I can say F1 prime, but anyway, this F2 is not a fundamental, it's not the second harmonic, but it's the fundamental or the first harmonic of the string 2, okay? Just keep that in mind. So V divided by 2L2, 34.2 meters per second divided by 2 times of that 86260 meters. So this gives me my fundamental frequency to be 198.2 hertz. Okay, so the beat frequency then will be the absolute value of the two, F1 minus F2. Okay, so 212 hertz minus 198.2 hertz. Okay, that would be 13.8 will be the beat frequency. Now B is asking you if this one is a little bit longer, so then the beat frequency will increase or decrease. So if this is longer, this guy will be larger, right? So if this is larger, then F2 will be smaller, okay? Now F2 is being the smaller one of the two frequencies, so then if this becomes smaller, then beat frequency should increase, okay? So according to that, we should say it should increase, right? But then let's take a look on the actual number in part C. So just repeating what we did in part A, okay? So basically we'll start from there. So L2 now is L1 plus the new delta L, 0.08066 meters plus 0.00760 meters, okay? 0.08827 meters. Then F2 being calculated. say prime, L2, let's put a prime there as well. So it's 34.2 meters per second over this new number, 8.08827 meters. So it gives you 193.7 hertz. Then the beat frequency, F beat prime, F1 minus F2 prime, okay? 212 hertz minus 193.7 hertz. So that gives you 18.3 hertz as the new beat frequency. Okay. All right, and let's go back to the slide. Switch back to my camera. All right. So in the lab, we did something like this. We have a vibrator, right? That is controlled by the sine function generator, and then we create different loops. And then the tension in the string was achieved by hanging masses. Okay, so that's what we did in the lab. So in this case, we have kind of the string two ends are fixed, one by the vibrator, the other one by the pulley. Okay, so the total length would be the L is shown in the figure. Now, what happens if you have just one end being fixed at the vibrator and then the other end being actually free to move? Okay, so then once you generate a wave here, because this end is free to move, so actually it will vibrate at maximum. So then you'll get actually an anti-node on that, but you'll have a node on the end of the string that is fixed. Okay, so a node here, an anti-node. And then you'll imagine, so this will be then just 1/4 of the whole wavelength because node, anti-node, node, anti-node, and then node. That's a complete wavelength. So this is 1/4 of the whole wavelength equal to L. So then lambda equal to 4 times of L. Okay, so in that sense. So the scenarios you could have is the first one being the harmonic being the fundamental. So it will be having wavelengths of 4L divided by 1. And the frequency will be V divided by 4L, okay, in that case, and then 1 should be in front. Now the second scenario you can imagine is because this end is fixed, so it's a node. So this one should be an anti-node, okay? So in order to have an anti-node, because node and anti-node are in alternating pattern, so node, anti-node, node, and anti-node. Okay, so then this is the second scenario. So in this case, the wavelength, the total length will be just equal to 3/4 of the wavelength. So then the wavelength will be so 3/4 of lambda is equal to L. So then you flip it, right? So lambda then is equal to 4/3L. So in this case, so this is 4L/3, and this one is 4L/1. And you can look at the next scenario. So it turns out to be 4L/5, and then this will be 4L/7. Okay, so then we just call this as nth harmonicas, the n being the odd numbers. So 1, 3, 5, 7, 9. Okay, so then you can have 4L divided by n for each of the lambdas. And then the frequency then will be n times of the fundamental V over 4L. Okay, so 1, 3, 4, 1, 3, 5, 7, 9 in that sense. Okay, so with one end fixed, the other end being open, the wavelength will be equal to 4L divided by n, n being 1, 3, 5, 1, 3, 5, 7, the odd numbers, okay? The fundamental frequency then will be n times of the fundamental, or the nth harmonica frequency is the n times of the fundamental times F1, okay? Which F1 being V divided by 4L instead of V divided by 2L in the case of the two ends are both fixed. All right, so now let's switch gear to another wave, standing wave. This is the standing wave in air columns. So you can do this pretty easily at home. So if you have identical bottles, you can fill them with different height of waters. Doesn't have to be colored water. Okay, so just pure waters and then blow air on top of the bottle. You'll hear actually different tunes. So this is then you generate the standing waves in the air columns in these bottles because they are having different lengths for the air columns. So then the different harmonic you generate, the frequency are different, right? So then you hear different tunes. So that's how organ pipes works, or any of the other like instrument that you actually play that requires you to blow air into it or on the top of it. Okay, so for example, flute, drums, you actually generating the standing waves in air columns in the drum. Okay, so in that sense. So let's take a look at this air columns. The first scenario is you have one end of the air column being closed, the other end being open. So if you blow air on the top here, you can see at the open end, the air molecules will vibrate at maximum, right? So then you get antinode there. But on this end, the air molecules will actually vibrate at minimum. So this is a node and antinode. The second scenario will be node, antinode, node, and antinode. Okay, so in that pattern, then the third one will be this. So the wave you generate in this scenario is something very similar to the string with one end fixed, the other end being open, okay, or free to move in that sense. So then you have first harmonic, third harmonic, fifth harmonic, just as what we saw earlier for the string have one end fixed and then the other end free to move, okay? And then the equations are the same as well. Now, if you have both of the end of the tube being open, then you get antinode on one end, also antinode on the other end. So then you'll have a node on the middle to start with. Okay, so this is then the first harmonic. The second harmonic, you'll have antinode, node, antinode, node, and antinode in that sense. So this is a quarter of the wavelength, and then half and a quarter. Okay, so this then add up to be one full wavelength. So this one is half. A quarter plus a quarter would be half. Okay. This is like half loop plus half loop, which is one full loop is half of the wavelength. Now this is half loop, one loop, so two loops, okay? So that's one full wavelength. And in this scenario, you have one, two, and then half, so three loops. So then the total length will be equal to three halves of the wavelength, so in that sense. So this is actually similar. The formulas are the same as when you have the string have both sides fixed, okay? So then the first harmonic, second harmonic, third harmonic, etc. All right. Another scenario is if you have like drums, right? So then both ends are closed. So air will be vibrating minimum at both ends. So then you get node here and node there, okay? And then the second scenario will be something like this. The third one will be like this. So although it looks a little bit differently, but this is half of the wavelength, and then this is a full wavelength. This is three halves. So similar to this scenario, you have first one being full, half of wavelength, full, and three halves. Okay. So then the formulas are the same as the previous one. Okay. All right. Let's take a look on the example here. So it says you have organ pipe both open at both ends that has a harmonic with a frequency of 440. And the next higher harmonic in the pipe has a frequency of 495 Hertz. Find the fundamental frequency of the organ pipe and then the length of the pipe. Okay, use the speed of sound being 340 meters per second. So this is the pipe with two ends open. So it's this scenario. So then you have the harmonics equal to F sub n, nth harmonic equal to n times F1. Okay. So, and then F1 is equal to V divided by 2L. Okay, so I think we'll be using those two equations here. Let's take a look. So what you will be writing down here is the nth harmonic, F sub n, F sub n is equal to 440 Hertz. Now, the next harmonic, that means n plus 1. 495 hertz. And Fn is equal to n F1. So basically it says this is equal to 440 hertz. So then apply Fn plus 1 will be n plus 1 times F1, which is 495 hertz. Okay, so let's look at these two equations. So let's say equation 1, equation 2. So there are two unknowns of n and F1, n and F1 being the two unknowns. You have two equations. So you can solve for both. Okay, so you can do substitutions, or in this case, actually, it might be easier to look at the second equation. So the second equation distributing F1 into the parentheses, you actually get n F1 plus F1 equal to 495 hertz. Now n F1 is 440, so then this guy is 440. Okay, so 440 plus F1 is equal to that. So F1 then equal to this one minus that, right? So 55 hertz. So you can get that directly. Okay, so now you have A solved. Now for B, because F1 is equal to V divided by 2L, so then L is equal to V divided by 2F1. So use V as 340 as instructed in the problem, 2 times 55 hertz then. This gives you L equal to 3.09 meters. Okay, so that's the length of the organ pipe. All right, so we'll stop here, and then we'll come back for the reminder of this. I think we are done with this chapter, so we'll come back to chapter 17 next time. Okay, bye.